Okay, so question 3 says, given that the thermal conductivities of wood, straw, insulation, and drywall are 0.12, 0.09, and 0.17 watts per meter degree C respectively, determine the rate of cooling of a 25 degrees Celsius room on a 10 degrees Celsius day through a 10 square meter wall constructed with a ½ inch of drywall, 4 inches thick straw insulation panels, and a 1/4 inch of cedar siding. And the answer ends up being 1.2 watts. So this is the question that was actually the reason I decided to do the homework with you this week in the videos. This is a pretty hard question, and I think it would be legitimately confusing to figure out what we're talking about and what you need to know and everything. So I wanted to give you a little bit of background to help this out. So the first thing is that I want to think about the amount of heat transferred and the speed with which it's transferred. So you could write down an equation that Q equals the rate of transfer times the amount of time that is being transferred. This is a restatement of something that I think is pretty familiar. This is distance equals speed times time. That's really all that's saying. We've got a total amount that something changes. That is the amount of energy transferred. We've got a speed, that's the rate at which it is being transferred. And then there's the amount of time through which it's being transferred. That's the relationship between the amount, the rate, and the amount of time. Okay, when we're talking about energy, we often, for the rate, we call the rate P for power. So we're going to rewrite this as Q equals P times delta T. And to remind you that Q is the amount of energy transferred. So heat is energy transferred. We've got P, that's the rate at which the energy is transferred. That's also called power. It's a rate. And we've got delta T, that's the amount of time that it's happening. All right. I'm going to rearrange that equation again to express something about the power. So the power, or the rate at which heat is being transferred, is equal to the amount of energy transferred divided by the amount of time during which it's being transferred. Okay, so then if you look on page 15 in the online materials, you will see an equation there that says P equals K A delta T, that's a big T, over D. So this is expressing something about the rate of energy transfer through materials. And I'm going to unpack what all those things mean. So the K is called the thermal conductivity. And it's kind of like the specific heat in the other question. It tells you how quickly something transfers energy. So something with a high thermal conductivity transfers energy very easily. Something with a low thermal conductivity does not transfer energy very easily. And that's what these numbers are up here. So we've got a K for wood. Hold on, let me make that red so it's easier to see. So we've got a K for wood of 0.12. We've got a K for straw insulation, so of 0.09. So the straw insulation is not quite as good as at conducting heat as the wood. And we have drywall, I'm going to call that one KD, that is a higher conductivity. So of these three materials, and let me back up for a moment. When you're building a wall, you want to have a really low thermal conductivity because you want to be able to keep the inside of the house warm when it's cold outside. And you want to be able to keep the inside of the house cool when it's hot outside. which means you need to maintain a temperature difference between the inside and the outside, which means you want it to be very slow to transfer energy through the walls. So you want low numbers here. So the drywall is the worst at that. The straw insulation is the best, and the wood is kind of in between. And because you have to make a wall out of more than one material, you have to combine those conductivities. So, yeah, so you put these materials together in order to create a thermal barrier, and not just a physical barrier, between the inside of the house and the outside of the house. All right, the A is the area of the wall, or the area of the material. So it kind of makes sense, I think, that if you have a larger area of wall, you're going to transfer more energy through that wall than a smaller area. So more surface area in contact with that big temperature difference is going to transfer energy more easily. Then we've also got delta T. This is a big delta T. That's the temperature difference. Kind of just like for the specific heat question a moment ago. So this is telling you that if you have a big difference in temperature between the inside and the outside, it transfers energy more quickly. This is actually called Newton's law of cooling, and Newton had more laws than just the motion ones. And he figured out this relationship between the rate at which energy is being transferred and the temperature difference. So this is saying that if there's a huge difference in temperature between the inside and outside, it's really hard to maintain the temperature inside the house. But if there's a small difference in temperature between the inside and outside, it's not so difficult. And you can see that like when it's winter and it's very cold outside, your heater in the house is on a lot in order to maintain the nice toasty temperature that you like inside. Or if it's really hot outside and you have the air conditioner on, the air conditioner is on a lot in order to maintain a cooler temperature inside. Okay, and then there's one more piece. The D is the thickness or distance of the material. And I think it would make sense that a thicker material is going to transfer energy less easily, and a thinner material will transfer energy more easily. So the reason the D is on the bottom of this is that the thicker the material, the slower the rate of energy transfer. So you can see the K and the A and the delta T are all on top of this fraction. That means as those get bigger, the rate at which energy is being transferred through the material goes up. The D is on the bottom because as that gets bigger, the thickness of the material gets bigger, you get slower energy transfer. So I'm going to do two calculations here. One, I'm just going to figure out the power rate for one of these pieces of material. So I'm going to do the power rate for the wood. We're going to plug in these numbers. So we've got 0.12 watts per meter degree C times the area of the wall. It's a 10 square meter wall, so 10 meters squared. We've got a delta T, that's the temperature difference between the inside and the outside. So it's 25 degrees inside and 10 degrees outside. So what direction is the energy going to flow? It's going to flow out of the house. So we've got a negative 15 degree temperature difference, degrees C. And then on the bottom of this fraction, we've got the thickness of the material, and we see it's 1/4 inch cedar siding. So that's the thickness of the wood. So 1/4 inch, 0.25 inches. Okay, so there's going to have to be a little bit of unit conversion. The inches are going to have to be transformed into meters. But then once you do that, you would take the 0.12 times the 10 times the negative 15 divided by whatever number ends up on the bottom of this, and you get the rate of power transfer, the rate the energy is transferred through a wood wall that is a 1/4 inch thick. Okay, so hopefully that helps you to understand a little bit more about what's going on in this question. But there's one more complication, which is even more the reason why I felt like I needed to go over this question. And that is that you've got three materials put together. So we've got the wood, the straw, and the drywall. The wood is 1/4 inch thick, the straw is 4 inches thick, the drywall is 1/2 inch thick. I can't just add these power rates together because that would make it look like putting the materials together transfers energy more easily, but it should be slower. The more of those pieces I put in there, the slower the rate of energy transfer should be. So just to draw this a little better, we've got several layers of material in here. We've got the wood on the outside. That's the cedar siding. Goodness, it's hard to write sideways. And then we've got the insulation panels. That's the straw. Let me not write sideways this time. In the middle, and then we've got drywall on the inside. So the energy to cool the house from the outside has to flow out of the house. We've got hot inside, cold outside. And that energy has got to flow through all three of those materials, and each one of them is going to slow it down. So we've got energy going through the drywall, then through the straw, then through the wood, and then out, and that will slowly cool the house down, unless you have a heater on inside to keep it warm. So we've got to figure out how to combine those three different rates together to get the combined rate. So there's another formula that was on the bottom of that page 15 that says if you've got a combined material, you've got to add it in a funny way. So the power rate for multiple materials is the area times the temperature difference divided by what you get by adding up the pieces from each. So there's d1 over k1 plus d2 over k2 plus d3 over k3 plus ... If there were more materials than just 3, you would keep adding more terms. So you've got the area and the temperature just like before. That matches with what we saw up above in the original formula. So you've got the area and the temperature difference, but the k kind of moves down to the bottom of the fraction, and the d stays on the bottom. So you've got a bunch of terms which are the thickness of the material divided by the thermal conductivity plus the thickness divided by the thermal conductivity plus the thickness divided by the thermal conductivity. You add those all together and you get the total rate. Divide that by the A delta T and you get the combined rate. So I'm not going to do all the plugging in for that. What you're going to have to do is you're going to have to plug in the distances, the thicknesses of the materials, and convert them all into meters. Put the K's in the right places and divide it up to get the combined rate. And when you're done, you should get 1.2 watts, 1.2 joules every second. So I hope that helps. Be sure to ask questions through the comment features if you need any clarification.